Now let's talk about the subtraction operations. Okay, so let's see what a subtraction means. And also in that process, we'll just start with the assumption that these binary values are all represented using 2's complement format. So using 2's complement format, the claim is there is no need for additional subtraction circuit. We can use this following, like a minus b is practically your a plus with minus b. Okay, so let's say I have two quantity a and b. We are trying to do subtraction between them. So it is same as saying we have two quantities a and minus b, and we are doing addition between them, right? Algebraically, it's a good claim. It's a right claim. Now minus b, like I have an amount. Let's say, for example, I have an amount 15. Okay, 15 in a 8-bit 2's complement example. I have an amount 15, b equals 15, and I have another amount a equals 5. Okay, so I want to do a minus b in 2's complement format. So 5 minus 15 results in minus 10, right? Now that I can say as it's a 5 plus minus b, minus 15. Now what all I need to do is to be able to represent the 15 or convert the 15 into a minus 15 pattern, right? So 5 minus 15 I want to do. So my two quantities were 5 and 15. All I need to do, convert this 15 into minus 15 and do addition. So how can we do that? It's a logically, it is very straightforward. You basically take inversion of the original pattern. Okay, let's say 15 has a pattern like 1 1 1 1 1 1, right? 1 1 1 1, that is the 15. And in 8-bit, it in terms of 8-bit, it becomes 0 0 0 0 1 1 1 1. So minus 15 will be represented by inversion of that bit pattern, which is like 1 1 1 1 0 0 0 0, and add a 1 on top of it. So that becomes 1 1 1 1 0 0 0 1. Okay, so that 1 1 1 1 0 0 0 1 represent minus 15. So we got a bit amount like 15, for example. What all we need to do, make a minus 15 representation, a bit representation, which can be easily done in 2's complement format. Like if we assume all these bits are represented in 2's complement, what we can do, from a given amount, we invert all the bit and add one top of this on that change inverted bit pattern. So that's easy. That means all we are doing is this. You take that binary replicatory adder circuit as a beginning carry in stage, instead of 0 make a 1. Okay, so that will take care of that extra plus 1 here. Like we have a plus 1, a plus inversion of b plus 1. That first stage carry in set to 1 will take care of that extra plus 1, and all we need to do is to insert some inverter circuit from register B as compared to our original binary ripple carry adder. As soon as we do that, this modification in the circuit, we have a binary ripple carry subtractor. Okay, is the same thing. So these will become your subtraction circuit. Now if you see, the difference between an adder and subtractor is two things, right? One is presence of this inverter in the circuit and the initial carry in value. For adder it is 0, for subtractor this is 1. Now we can combine it, right? So we have, let's say, two things to do, addition or subtraction. Let's say there is a control signal called SNA. So for this, if this SNA logical value is 1, it is a subtraction operation. If the logical value is 0, it is an addition operation. So what we can do, first of all, we can directly feed this control value to the first stage carry in, because your subtraction need 1, carry in 0. Subtraction mode determined by SNA, this digital signal is 1, so that part goes directly in the CI, and SNA becomes 0 for the addition, and 0 is added into the CI directly to make an adder circuit. So that part is done. And now, depending on this value of SNA, we have to select either complemented form of the B or uncomplemented form of the B. Okay. So we can definitely deploy a multiplexer. That's an hardware decision making component, as we studied that component, about that component in few lectures back. So we are connecting SNA as a selection logic or selection value of all these multiplexers, and so upon 1 it should take the inverted value, upon 0 it should take the non-inverted value, and by connection we are achieving that functionality. Now this becomes your Adder-Subtractor. So this whole digital circuit, just by telling it whether I want to do an addition or subtraction, I can pick up values from this register C, S3, S2, S1, S0 as their sum bit or subtraction bits, depending on what I requested. If I set SNA to 0, it is an addition, it become addition. If an SNA is 1, it is a subtraction. Now next challenge here is this, like we are looking at a little more complex circuitry here, right? Especially the selection circuit. If you think of this multiplexer, like it has like what? It has inside like one little decoder, 1x2 decoder, and then it has this AND gate of selection logic and an OR gate and so on and so forth, right? So, and also you can probably use some enable circuit in it. So we are talking about lot of gates needed as we are using multiplexer in our circuit, in this circuit. Challenge is, can we simplify it? The answer is yes. All we need to do a little deeper study on their logical relation between each of these bits. Okay. Let's focus on one of the bit, like B0. Okay. This B0 can have a value 0 or 1. Okay. Just let's try to do some logical thinking here. Let me just bring up a notepad. Okay, so this is good. All right, so what I'm saying, let's say this B0, look at this B0. B0 can have a logical value of 0 or 1, right? And then the 1 going into the B port of the full adder, first stage full adder, let's call it a like full adder B. Okay, depending on S and A signal, the value will be changed, right? So if S and A was 0, you need to feed a 0 into this B port of the first stage full adder circuit, right? Because it is an addition. if let's say b was 0, SN1 is 1, means I'm doing a subtraction here, your b port has to fade with 1. Now b0 is 0 again, and I'm doing an addition. I have to feed in non-inverted in form of that b0 bit into the first stage of first stage full adder, the p port, and same b0. If I'm doing subtraction now, SNA set to 1, I need to feed a 0 here. Now look at the truth table. Isn't that your FA B equals B0 XOR, I cannot type in that XOR symbol here, just we can type here like XOR as a word, S and A, right? So by looking at the simple logical relation between the bits and the S and A different combination and what we need to feed into B port of the full adder, we just determine they have a XOR relation between them. That means we can change the whole circuit, simplify the whole circuit like this. We deploy a bunch of OR gates, like 4 OR gates in this context, and then one of the input for all the OR gates is your S and A, your mode, and other input is their individual bits from that register B, and that output of the XOR being fed into the B port of all this full adder of this ripple carry adder circuit. So this guy will take care of either inversion or the same non-inverted value to be fed into the full adder depending on which mode you are choosing, whether you are choosing an addition by setting SNA to 0, or you are choosing subtraction by setting SNA to 1. So in digital circuit and logic world, we always think to simplify our circuit as much as possible, because these are all small, very small components, small portion of the entire chip you can think of. Simplify, we make the basic circuit simplification, more simplified processor it would be. It has an advantage of like simplifying, simple circuit has an advantage of being like easy debuggable. If there is a problem, we can easily debug. We can compact the circuit footprint, that means like less amount of semiconductor material is needed. That means it's going to reduce your product cost. Okay, so that's why we always think simplification, right? We started with a complex one just from the spec and our first initial intuition that, hey, we have this hardware selection capability to multiplex and let's use it. But we also readily realize this thing has many basic level logic gates, many extra transistors there compared to if we just look at the logic relations between different components of any digital circuit. We should be able to figure out a simple relation, simpler circuit, logic circuit for a given purpose. In this case, which becomes just a bunch of XOR gates, and that's all. So please keep that in mind when you do a digital logic circuit design. In any case, like in your real life, if you pick up that kind of job, this is your primary goal, to make circuit better and better and better by simplifying it.